Welcome back. So let's now use the concepts that we have learned to solve some fluid pressure problems. I have a gravity dam here, which is made of concrete, and this gravity dam is held in place by its own weight. This little orange block here that is fixed to the ground at point A, it's there to avoid the slipping of the dam in the forward direction due to the pressure that this water here is applying to the dam. You can neglect the height of this little block. It's very tiny. Now the density of the concrete, let's call it rho C, is 2.5 megagrams per cube meter. Then water has the density of 1 megagram per cube meter. Essentially, it's 1,000 kilograms over cube meter. And also, rho C is 2,500 kilograms over cube meter. The total depth of water that the dam is holding back is 6 meters. Your task is to determine the smallest dimension d that will prevent the dam from overturning about its end at point A. So if d is too small, then the pressure from water will simply overturn this dam about point A. What is the smallest d that will prevent the dam from tipping over about point A? So here's the thing about fluid pressure. You mainly have two types of fluids: liquids and gases. Liquids are assumed to be incompressible fluids. It means that the density of a liquid does not change significantly with pressure. So for example, here you have less pressure than here, but the density of water will be 1,000 kilograms per cube meter in both places. In reality, nothing is 100% incompressible. But when it's very small, then you can still assume that. In that case, you can use the following formula to determine pressure at certain depth inside water. Pressure P equals the density of the liquid times the gravitational acceleration times z. And note that here we assume that z becomes bigger as you go down, as your depth increases. So positive z is downwards. This P here is pressure, and it's measured in pascals or newtons over meters squared. Then the density of the liquid, it has kilograms over cube meters. G is of course meters per second squared, and Z is in meters. That's your depth. This is called the Pascal law, and as you can see, if the density of the fluid and G are constant, which is our case here, then pressure depends on Z linearly. So this here, rho times G, it would simply be a constant. It's simply a linear function here. Also, according to the Pascal's law, the direction of pressure is always normal to the surface of the object inside the fluid. So in our case, our pressure equals 1000 times G times Z, and it's perpendicular to the wall. So the bigger your depth, the higher your pressure. And just to specify that this pressure distribution is in pascals, so in newtons over meters squared, and not in newtons over meters. Just to clarify that. In other words, it would be more correct to think of the dam in 3D, and the same thing with pressure distribution. When it's in pascals, then this pressure is being applied to this two-dimensional wall of the dam, no matter how wide that dam actually is. You don't need to know in this exercise though. So in general, if I have a plate underwater, even if it's at an angle, then if we take this side here, then the pressure would vary linearly with depth, and it would be normal to the surface. In other words, it would be perpendicular to the surface. Note that we're only considering one side of the plate, but of course you will have pressure on other sides as well, like for example on this side, and then you have the same thing on this side and on this side. Note that this arrow here, it has the same length like this arrow here. That's because they're both applied to the same point. In both cases you have the same depth. That's why these two arrows have the same length. They have different directions because they're always perpendicular to their surfaces, but the pressure is the same in this location for both arrows. Then you see that this arrow here, it's slightly bigger because this corner has a bit of more depth, but it has the same length like this one here because they are both applied to the same point. Just like this arrow here has the same length like this arrow here. And then this arrow, which is slightly longer, it has the same length like this arrow here. Because in both cases, you have the same z, and well, the water density and the gravitational acceleration is the same for all the points on this plate. And again, it's all in pascals. Or for example, if I have this curved plate, then again, the magnitude of the pressure changes with depth linearly, but it also changes the direction because it's always normal to the surface, and the plate always changes the direction itself as well. But of course you have pressure from all sides. You already know that this arrow here, it has the same length like this arrow here because they have the same z value. This arrow is slightly longer because the z value is slightly bigger here, but it's equal to this length here. Then this length here, it's equal to this one here, and then this one here is slightly longer, and it's equal to this one here. Note that this law, P equals rho gz, it's only valid for incompressible fluids. Gases, on the other hand, are compressible fluids. Their density changes significantly with pressure. If you remember, then we had an exercise about a hot air balloon, and we had something called an equation of state, P equals rho RT, and so your density, it could be written down like this. As you can see, it would change significantly with pressure. That's why this law here, the Pascal's law, it cannot be used for gases. So in this fluid pressure part, we will deal with incompressible fluids, mainly water. Welcome back. Here I would like to derive the Pascal's equation to show you where it comes from. Imagine that you are inside water. We will choose an imaginary section inside that water that we mark with this dotted line. In 3D, it's a cuboid, which is a 3D rectangle. You have the x and the z dimensions, and then the y dimension goes into the screen. Now this cuboid has the dimensions of delta x, delta z, and then in 3D you would also see delta y. And so this volume inside the water, it's in equilibrium. It's just water. And this dotted line, this cuboid, it's our imaginary volume. On top of this volume, you have pressure 1. In the bottom of this volume, you have pressure 2. This cuboid, it also has some kind of force of gravity. Since this cuboid is in equilibrium, we can write the equilibrium equations for it in the z direction. And so the sum of the forces in the z direction would be 0. And so you would have pressure 2 times delta x times delta y. That will give you this lower area here. And then if you multiply it by pressure 2, you get your point force up due to pressure 2. Then minus pressure 1 times delta x times delta y. So it would be this area here times pressure 1. And then minus your force of gravity. However, you can rewrite it like this. Minus the density of the water times delta x times delta y times delta z and times g. This here, that's the volume of your cuboid. Then this one here, that's the mass of the cuboid times g. That would give you your force of gravity or your weight. And so all that has to equal 0. If I now divide everything by delta x times delta y, then of course you can make cancellations and you will end up with pressure 2 minus pressure 1 minus the density of water times g times delta z, and that will be 0. And so you can see that the pressure difference here, that's your Pascal's equation. You can see that it's a linear function. So in this drawing, you can see that this is a linear function that varies with depth. And now, if we only consider the pressure due to water, meaning that we don't include the local atmospheric pressure above the water, then at 0 depth, your P1 would be 0. So this is pressure due to water only. And so instead of this equation, the pressure due to water at 0 depth is this one. And then instead of P2, we can have a general variable for our pressure. So you will have pressure equals this times this times this. So as you move down, your pressure increases according to this equation, but now you can see where it comes from. Thank you very much. Welcome back. In addition, in this gravity dam exercise, you will have to calculate the center of gravity for this dam in this cross section. So now what we are doing, we are taking the cross section of the dam and we want to calculate the center of gravity for this cross section. So we are not concerned with finding the center of gravity along the width of the dam, but rather we are taking a cross section of that dam, which in our case is the same everywhere. We have the cross-sectional area of the dam and we try to locate the CG in that cross-sectional area. Now, since the gravitational acceleration g and the density of the dam rho c are constant, that means that the center of gravity of this cross-section equals the center of mass of this cross-section and also the centroid of this cross-section. So we might as well just find the centroid of this cross-section, and that will also be my center of gravity. So how do you do it? Well, here's how you locate the centroid of an area. I take this cross-section and I place the lower left corner at the origin of my xy coordinate frame. So let it be O. Then since my depth here is 6 meters, that means that I have 6 here. And then my horizontal length is d meters, so let this one here be d. And now this diagonal line here, it can be written in terms of a function. Y as a function of x equals 6 minus 6 over d times x. This 6 is the place where this line crosses the vertical axis, the y-axis, then minus 6 over d, that's the slope of this line, and it's negative because the line goes down. And so that's the function. Then you compute the area of the cross-section. Now in this case it's easy, but let's use integrals in order to generalize it a bit. You can have a differential element here. Here you have dx, then this one is y over x, and so your differential area equals y as a function of x times dx, and so it's this differential area here. I put here small x because later on, in order to calculate the centroid, I will also have this differential area, and I will call that day. That's why I'm going to put x here. And so the area of the cross-section is when I sum up all these differential areas in this cross-section. So I can rewrite it like this: the integral from x equals 0 meters till x equals d meters, because I go from 0 till d, and then I have y as a function of x times dx, and so now I'm just going to put this function right here, and then times dx. I can also write it out like this. Note that even though I have to find d, right now I'm assuming that I know my d, so I'm treating it as a constant, and that's why it's outside of the integral. And so if I evaluate this integral, then I will have this thing here, or this thing here. I can cancel out the d and the power, so I will have 6d minus 3d, which is 3d meters squared. Essentially, it's the area of the triangle. It's 6 times d over 2, which is 3d, but that's the general way to get it. You can use this way for more complicated shapes as well. And then, in order to get my x bar c, which is the centroid of this cross-section in the x dimension, you have to take this dax that you have here, and you have to multiply it by the distance that separates this dax from your y-axis. In other words, you have to multiply dax by x, and you have to do that for all the differential areas in this cross-section, which means that you have to integrate this product. But you know what your dax is, so you will have an integral from x equals 0 meters till x equals d meters, and then x times y as a function of x times dx. In other words, you will have x times then this function and dx. Let's call it my, since this x is the distance between the differential area and the y-axis. Then you take the area of the cross-section, and if you multiply it by the centroid of this cross-section in the x direction, you will need to get this integrated product. So x bar c equals my over a, and so you have this integral over this integral. So that's x bar c. To find y bar c, the centroid of the cross-section in the y dimension, you do it in a similar way, but I will let you do it by yourself. So you have two tasks. Task number 1, find x bar c and y bar c, and secondly, what is the minimum d that still keeps this dam from tipping over about point A. Try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. So let's now solve this gravity dam problem. We first need to find the centroid of an area of this cross section here, x bar c and y bar c. And then we had to find the minimum distance d that would still keep this dam in place and not allow it to tip over about point A. First of all, you know that x bar c equals all this. And you know that this is the area of the cross section. And so let's evaluate this my. So my equals this integral, which you can rewrite like this or like this. This is its evaluation. In the end, you get this thing. You can cancel out the d here, and this 3 power will be 2 power. And in the end, you will have d squared meters squared times meters, because remember that you have x times dA. This is meters squared, and this is meters. So in the end, you will have meters cubed. And so in the end, x bar c equals my over a, d squared over 3d. The area was 3d. Then this d here get cancelled out with this power, and you will be left with d over 3 meters. So that's x bar c. Now we have to find y bar c. For that we have to integrate in the y direction. So I have a differential element here, and then right here I have dy. And now if this is my y as a function of x, then what I need is x as a function of y. So you have to take the inverse of this function. So you can rewrite this function like this. 6 over d times x, and then you have 6 minus y, then x equals 6d over 6 minus yd over 6. So you cancel out the 6's here, and that means that x as a function of y, it's d minus d over 6 times y. And that's this distance here, x as a function of y. So dy equals x as a function of y times dy. So it's this differential area here. And now, if we sum up all these differential dy areas, where you would integrate from y equals 0 till y equals 6, and then here you have x as a function of y times dy, obviously it will give you the same area, 3d meters squared. You can check that. This will be your integral. You can rewrite it like this. In the end, you will have this result. So you will have 6d minus 3d, and so you will have 3d meters squared. As you can see, the same thing. Then, what you need to do, you need to take this dy and multiply it by its distance from the x-axis. You have to multiply it by y. And so you will have y times dy. Then you have to do it for all the days. In other words, you have to integrate this product. In the end, you will have this integral. You can rewrite it like this. This will be the result. I take away this 6, and then here I put 2. So I have 18d minus 12d, which is 6d cubed meters. And let's call this thing, this integrated product, mx. And now y bar c, that's mx over a, 6d over 3d. You cancel out the d's, and you will have 2 meters. And there you go. The centroid of this right triangle cross section is at d over 3 and 2 meters. So d over 3 is somewhere here, then 2 is somewhere here, and so this point here, that's your centroid. And since we assume constant density and constant g across the dam, that point is also our center of mass and center of gravity, which means that force of gravity goes through this point in this two-dimensional cross-section. If we had varying density and varying g, then of course the center of mass and the center of gravity would be in different locations. Another point that I want to make is this. So this is our right triangle. This distance is 6. This was d. This was d over 3. This was 2. And so this is your centroid, your C. Now note that just like here, you took your d and you divided by 3. Here you took your 6 and you divided by 3 and you got 2. And so the general rule for right triangles is this. If you have a random right triangle, and let's say that instead of 6 you have here C, so this side is d meters and this side is c meters, then the centroid of a right triangle is always this one. From this corner here, you go d over 3 meters this way and c over 3 meters this way, and that's the centroid of a right triangle. We did it with 6 meters, but if instead of 6 meters you had used c, then you would have gotten c over 3. So that's how you get the centroid of a right triangle. Welcome back. So we have our centroid and also our center of mass and center of gravity for our cross section, and you will see why we needed that in the first place. Let's now calculate the minimum d that will keep the gravity dam in place. The function of the pressure that the dam experiences is in pascals, so in newtons per meters squared. However, what I want to get is newtons over meters. And so if we say that this is the length of the dam, even though in the past we referred to it as the width, but let's refer to it as length now. It doesn't matter. And so I will take my pressure function P and I will multiply it by L, whatever it might be. So P is newtons per meter squared, L is in meters, and as you can see, I will get W, which is newtons over meters. So it will be 1000 times L times G times Z, newtons per meter. And now here's the thing. The water will exert this pressure on the dam, and that distributed load has a center of pressure. We can equivalently represent this distributed load with a total point force Fw due to that distribution load that acts through this center of pressure. As you can see, there is a moment arm between Fw and A. Let's call it dV, vertical distance. That will create a moment about point A, which is Fw times dV. And that moment would cause the dam to tip over about point A. However, this moment is countered by another moment in the opposite direction due to the force of gravity of the dam and its corresponding moment arm that we can call dH, so horizontal distance. It will be in this way, Fg times dH. And that's why we needed this Cg. Thanks to that, we know that dH equals d minus d over 3. That's 2d over 3 meters. Remember, this part was d over 3, so this part must be 2d over 3. In fact, we only needed the Cg in the x dimension, but I wanted to cover both dimensions to give you a complete picture. And now what we need to do, we need to find the force of gravity, which is this one here, Fw and dV, for which we first need to find the center of pressure of the distributed load. The density of the concrete in the dam is 2,500 kilograms per cube meters. So force of gravity equals the density of the concrete, the volume of the dam, times G. This part here, it will give you the mass. You have the units of the density and the volume. You can see that the meters cubed get cancelled, and so you are left with kilograms. And then if you multiply it by G, then you get your force of gravity. And so all that equals 2,500 kilograms per cube meters. Then the area of the cross section was 3D meters squared, but then you multiply it by the length of the dam, and so you get the volume of the dam, that's in cube meters, and times G, which is meters per second squared. And so you will have 7,500 times D times L times G newtons, and that's your force of gravity. Then Fw equals, and now we will start going from the top in the downward direction. So at point B, your Z is 0 meters, and then as you go down, your Z increases up until 6 meters. So I will have from Z equals 0 till Z equals 6 meters, and then you have 1,000 times L times G times Z, and then I will have dz here. If you evaluate this integral, then you will have 18,000 times L times G newtons. And finally, to get this dV, I first calculate the total moment due to this force distribution about point B. So let me have the moment due to this distribution about point B. It will be the integral, and then Z times W times dz, exactly how we did it in the section on distributed loads. So this will be the integral, and if you evaluate it, you will have 72,000 times L times G Newton meters. And now Fw times Z bar, it's MWB, so your Z bar equals MWB over Fw, 72,000 times L times G over 18,000 times L times G. L and G's, they get cancelled, and so Z bar equals 4 meters. Now that's this location here. And so that means that dV equals, the total length is 6 meters. So I have 6 minus 4, which is my Z bar, and that's 2 meters. And so now you have two moments. You have this one here that we can call MWA, about point A, and this one that we can call MFG, about point A. You know that your Fw is this one here, and dV is 2 meters. So MWA equals Fw times dV, or 18,000 times L times G times 2 Newton meters. That would tip the dam over about point A. And then MFG about point A equals Fg times dH. So this is your force of gravity. It's this one here, times dH, which is this one here. So times 2d over 3, and that will give you 5,000 times L times G times d squared Newton meters. And this moment will counter the other moment, MWA, that's clockwise, and then the moment due to force of gravity, that's counterclockwise. And now, if the moment due to force of gravity is greater than or equal to the moment due to this pressure distribution, then the dam will stay in place. But if the moment due to force of gravity is smaller than the moment due to this pressure distribution, then the dam will tip over. So the minimum D here, it will be when the moment due to force of gravity equals the moment due to pressure distribution. So we're going to have this one equals this one. The reason why I have 36,000 here is because I take 18,000 and I multiply it by 2. So you have 36,000 here. Now we can cancel out the L's and also the G's, and so you will have D squared equals 36,000 over 5,000. In other words, D equals square root of that, which is 6 times square root of 5 over 5, and that's approximately 2.69 meters. And there you go. You have found the minimum distance that will still keep this dam in place. Don't forget to round this number up, because if you round it down, then the dam will tip over. If your D is less than 2.69 meters, then the moment produced from the force of gravity will not be able to counter the moment from this pressure distribution. Thank you very much. Welcome back. I have a wall here, and then on the left side of the wall, you have water here, and this wall holds the water back. And then I have the gate here, this AB section, that can rotate about point B. Right now, the gate is closed. The water that is held back by the structure exerts pressure on the gate AB. Now, the width of this gate is 8 meters. Due to the water pressure here, you have horizontal and vertical reaction forces in pin B, and the vertical reaction force at point A due to the normal force. The density of water is 1,000 kilograms per cube meter. And so your task is to find AY, BX, and BY. Good luck. Try it out on your own first, and then see the solutions in the next video. Thank you very much.